In this presentation, we're going to study projectiles in 2 dimensions. By projectiles in 2D, we simply mean objects which are launched with some initial velocity v0 and then which travel through the air without propulsion of any kind, that is, just under the acceleration of gravity, and we'll assume that here that the total acceleration will only be due to gravity, and moreover that it's perfectly constant. So we're going to neglect drag from the air. And we're going to neglect changes in gravity with altitude. And in particular, we'll assume that the magnitude of the acceleration is simply fixed at g, where g, by definition, is the acceleration of gravity near sea level, 9.8 meters per second squared. All right, before going further, let's begin by just exploring the qualitative behavior of projectiles in 2 dimensions. This window shows a simulation program that I've written using the mathematics platform MATLAB. This simulation program allows us to dial in different launch speeds, different launch angles, different amounts of air resistance, which we'll generally set to 0, and to launch from different heights above the ground. Let's launch our first projectile here with an initial speed of 20 meters per second. That is, the magnitude of the initial velocity vector is 20 meters per second. And we'll launch it at an angle of 30 degrees above the horizontal. Here we go. We see that the projectile traces out this nice parabolic trajectory. Now there are a number of parameters here that we would like to predict. For example, we might like to predict how far the projectile traveled. This parameter is called the range, and we can see that in this case the range was a little over 35 meters. We might also like to predict how high the projectile got, that is, the maximum height. And in this case we can see its maximum height was a little bit over 5 meters. We might also like to predict how long it took the projectile to make this journey. This parameter is called the time of flight. And if we look up here on the left, we see that in this case the total time of flight was about 2.04 seconds. We might also like to predict how long it took to get to the maximum height. This trajectory is very symmetrical, and it turns out that in this case the time to get to the top was just 1/2 of the total flight time, and we can see that up here on the right. T top was 1.02 seconds, whereas the time of flight was 2.04 seconds. And finally, we might like to know the speed with which the projectile lands. And in this case, according to what's written up here, the projectile landed with a speed of about 20 meters per second, which you'll notice was equal to the initial speed. And that's what happens when we have a projectile that lands at the same altitude that it was launched with. Let's now hold that trajectory and launch another projectile at a steeper angle, but keep the same launch speed. So we're still going to launch at 20 meters per second, but now we'll launch at 45 degrees. Okay, we can see that in this case, the projectile achieved a significantly higher height, but just a little bit more range. Let's go even steeper. 65 degrees. In this case, we again see the projectile achieved a greater height, but in this case the range actually lessened. And let's go to an even greater height. And we see once again we achieved an even greater height, but the range lessened even more. And this makes sense because as we approach 90 degrees here, we know that the range must eventually shrink to 0. Okay, let's go the other way. Now let's launch at an angle of, say, 20 degrees. Here we see that the range was less than it was at 30 degrees. And this makes sense because we're now launching at a very shallow angle, so the projectile doesn't go up very high, and that makes the time of flight very short, so it doesn't get to travel very far either. And let's go to an even smaller launch angle, just 10 degrees. And now we see that the range was only about 14 meters. Okay, let's clear that. Let's go back for a second to 30 degrees, and let's try launching with different initial speeds. So here we have the trajectory for 20 meters per second again, and now let's hold, and now let's increase the speed to, say, 30 meters per second. And we see just going up 10 meters per second took us a lot farther. Let's go to 40. And we see that took us a lot farther again. Okay, let's clear that. Now let's try launching at various heights above the ground. Let's set our launch speed back to 20 meters per second here again, and keep our launch angle at 30 degrees. And let's first run our initial trajectory once more. And now let's hold that. And now let's launch from a higher height above the ground, say 10 meters. We see that by raising it 10 meters, the first part of our trajectory looks very similar to the previous one, which it should. But now the projectile has substantially farther to fall, so it falls quite a bit below its initial launch point, and it travels farther as well. So it has a longer range, a higher height, but a similar path compared to the first one. Let's try a steeper angle, 45 degrees. In this case, we see that the projectile traveled almost the same range, just slightly farther, but substantially higher. Okay, you can get an idea from this that the relationship between the launch speed, angle, height, and range is fairly complex. And that's what we're going to try to do in this section, is calculate all these and try to understand the dependence of these various final parameters on the various initial parameters. Let's begin our analysis of 2D projectile motion now. We'll do so by looking carefully at what a projectile is doing at particular moments in time as it moves through the air. We'll begin the analysis process by looking at a few key aspects of what a projectile is doing at particular moments as it moves through the air. I'll start by sketching a pair of Cartesian coordinate axes to establish our coordinate system, which I'll label X and Y. And we'll sketch a trajectory here as well. Our projectile will have some initial velocity vector v naught. And this initial velocity vector must be tangent to this path right at the origin here. as the projectile moves through the air, it will have an instantaneous velocity at each point, and that instantaneous velocity will change as it travels. And it will always be the case that the instantaneous velocity is tangent to the path at each point. So for example, when the projectile is here, it will have an instantaneous velocity that looks something like this. And at the top, it will have a horizontal instantaneous velocity. On the way back down, it'll again have a instantaneous velocity, which is tangent to the path, but this time pointed a bit down. And then at the bottom, just before it lands, infinitesimally before it lands, it'll have an instantaneous velocity, still tangent to the path, and we'll call that v land. All right, now let's look at the relative lengths of these different instantaneous velocity vectors. At the beginning, our projectile has all of its energy in the form of kinetic energy. But as it travels upwards, some of its energy gets converted into potential energy, and its kinetic energy decreases, and so the speed of the projectile decreases, and that means the length of the instantaneous velocity vector must decrease. And you can see it's longer here than it is here, and longer here than it is here. On the way back down, however, the projectile's potential energy here is then reconverted back into kinetic energy. That is, assuming that we are neglecting air drag, and the speed of the projectile will then increase again. So the instantaneous velocity vector will become longer, and you can see it's longer here than it was here, and longer here than it was here. All right, so we sort of have this effect. Large instantaneous vectors here and here, medium size instantaneous velocity vectors here and here, and the smallest one right at the top. Now let's look at the components of these vectors, how they change as the projectile moves across. Let's begin with v0, the initial velocity vector. To find its x component, we project down, and we'll call the x component v0x. And to find the y component, we project over to the y-axis, and we have v0y. To find these components, we'll need to do some trigonometry, and we'll need to know both the length of the initial velocity vector, which we'll call just v0, and the angle at which it makes with the horizontal, which we'll call theta. And when we work out the trigonometry for this, according to the idea of breaking vectors down into components, we find that v0x is simply equal to v0 cosine theta, and v0y is v0 sine theta. All right, now, as the projectile moves through the air, it will work out that the y component of the velocity vectors change, but not the x component. Let's take a look at this instantaneous velocity vector right here. When the projectile is right here, it will have an x component of its instantaneous velocity, like so, and a y component, like so. You'll notice that if you add this vx to vy, you'll get back v. Okay, now, a very important fact is that vx here will still equal v0x. And in fact, that holds everywhere, all the way across the trajectory. So we can say that vx equals v0x at all times, and that it's constant, therefore. And the reason for this is because the acceleration only points downwards. And so it doesn't affect the x component of the velocity. The projectile, as far as its horizontal motion goes, just moves at a constant rate to the right. That is, as long as we can neglect the effect of air drag. But the story is different for the y component. You can see we had a large y component, v naught y, here, but as the projectile moves up into the air, the y component shrinks. So you can see vy here is a lot shorter than v naught y. And in fact, at this point, the y component is entirely 0. So at top here, and let's give this a name now, let's call that v top. We can say that v top y equals 0, and that v top x still equals v naught x. So in fact, at the top, the entire speed, that is the length of the instantaneous velocity vector, is just equal to v naught x. So we can additionally write that v, that is not a component, but the magnitude of this vector, v top, so it's v top without the arrow, v top just equals v naught x, as well as v top x. All right, now as the projectile comes down, then the direction of the vy component will change. When the projectile is at this point, for example, vy will be pointed downwards, but vx will still be pointing horizontally to the right. And then just as the projectile is landing, or infinitesimally before it lands, then we'll have a y component downwards, which we can call vly, and a horizontal component, which we can call vlx. And vlx must equal v naught x because the x components don't change at all. And it will work out in this particular case, where we're landing at the same altitude that we launched at, it'll turn out that vly, in this particular case, is equal to minus v naught y. In other words, the y component of the velocity has simply reversed sign as we've moved across. Now let's consider how we might actually write down equations for these x and y components of the velocity. Recall from one-dimensional projectiles that the so-called v equation was given by this. Well, when we're working with 2D projectiles, now we have to take into account that we have velocity components in two different directions, both x and y. So we can begin by simply affixing x's and y's to the v equations for both x and y respectively. All right, next, we now note that in fact the acceleration is only in the y direction, and since we have pointed our coordinate system upwards so far, then the way we represent this is by setting the x component of the acceleration to 0 and the y component to minus g. So this term disappears, and we simply have vx equals v naught x. the y equation, we have minus g, and v naught y will also be non-zero, so our vy equation becomes v naught y minus gt. And so we obtain, as our result for the y equations, that vx simply equals v naught x, and vy equals v naught y minus g times t. So this equation, this first equation for Vx, is fairly trivial. We basically just have to remember that Vx stays fixed at v naught x. The second equation is not trivial. We can see that Vy will change linearly with time, starting with its initial value v naught y. Now let's consider how to obtain expressions for the x and y coordinate of our projectile. And to see this clearly, we'll resketch our Cartesian axes here and our trajectory. And let's consider the moment when our projectile happened to be at, say, this point. Then we can locate its x-coordinate by projecting down to the x-axis, and we'll label this as x of t, that is, x at time t. Likewise, we can project over to the y-axis and label the y-coordinate as y at time t. Now we must find expressions for these. Recall that in one dimension, our x equation had the following form. So this was for 1D projectiles. The same form will apply here, but here we have to keep in mind a couple of things. First of all, we're launching at some non-zero angle here, and we'll have a v naught x component and a v naught y component of the initial velocity vector. But that initial velocity, those components, will change both with the length of the v naught vector and also its direction, and it will not necessarily be the case that v naught y will equal v naught x. So we're going to have two different v naught components. Likewise, our acceleration now points straight downwards. And that means that it has a non-zero y component, but a zero x component. In other words, a sub x is equal to 0, and a sub y, since we've picked our coordinate system pointing up here, a sub y will equal minus g. All right, without all of that in mind, let's now write one equation for our x component, or our x, the x component of our position, and we'll put a subscript here on the v naught to indicate that this number is only associated with the x component of the velocity, and we'll put a subscript x on the acceleration for the x equation, and for the y equation we'll have something similar. And now we utilize this information we discussed previously. First of all, we have to keep our v naught x and v naught y, because these numbers are essentially arbitrary depending on how we pick our initial velocity, both its magnitude and direction. But the x naught and the y naught in this particular problem can be set to 0, simply because in this particular problem we've set our launch point right at the origin, so that x naught equals 0 and y naught equals 0. So these are both identically 0. And as discussed before, ax equals 0, so this term is 0, and ay is equal to minus g. So, when all is said and done, we obtain the following two equations. For x, we obtain x equals v naught xt, which is a very simple equation. And for y, v naught xt minus 1/2 gt squared. Okay, now let's summarize all that we've obtained so far. For the x component of the velocity, we found that vx equals v naught x, which is just a constant. For the horizontal position coordinate x, we found that x equals v naught x times time, which just means that x increases linearly with time at a constant rate, which is consistent with the fact that vx equals v naught x. For the y component of the velocity, we found that vy equals v naught y minus gt. And that states that the y component of the velocity equals its initial value and then decreases linearly with time. For the y coordinate, we found that that equals v naught y times t minus 1/2 gt squared. And that equation states that y initially begins to increase linearly with time, but then this term will start to grow and grows quadratically, so eventually it grows faster or it gets bigger than this term, and this term causes y to turn around and come back down. So there we have it. Those are our basic equations of motion. We can also write a stopping distance equation for this problem. And we have a choice. We can write a stopping distance equation for either the horizontal components, so vx, x, and the acceleration in the x direction, or for the y components. It's not going to be very helpful to do it for the x components, because in this case the acceleration is just 0, and the stopping distance equation will actually just reduce to this statement up here. But when we write it for the y components, we do get something that's useful. And that comes out to be vy squared minus v naught y squared equals 2 times the acceleration, and in this case that's minus 2g, and then times the displacement in y. All right, and that gives us a complete set of equations for solving this particular 2D projectile problem. Okay, let's now put these equations to work with a concrete example. Let's begin by drawing our coordinate axes again. And let's consider the case that we first looked at with the simulation. Let's suppose we launch with an initial speed of 20 meters per second at an angle of 30 degrees. Okay, let's draw our trajectory here as best we can. And let's consider the kinds of things that we're going to ask. For example, we can ask, how high does the projectile go? That will be the y coordinate, so we'll ask what is the y-coordinate at the top. So we'll call that y-top. And we can also ask what time does it get to that position. So we'll call that t-top. We can also ask how far does it travel. That is, we can ask what is the range. And that's going to be given by the x-coordinate at landing. So we'll say xland ? To indicate that question. We also are going to be interested in when it lands, so tland. Finally, we can ask what is the velocity that it lands with. That is, what is the final speed, which we can call vland, and what is the angle that it lands at. So we have 1, 2, 3, 4, 5, 6 different variables to try to calculate here. All right, let's proceed. We need a strategy to do this. And if we look at our equations to the left, you'll notice these equations have Vx naught, Vy naught, Vy naught. So we need to calculate those quantities first, and then we can take a look at how we might ferret out the rest of these. So let's begin. By trigonometry, V naught x is equal to V naught cosine theta, which is equal then to 20 meters per second times cosine of 30, and we'll compute that in a moment. V naught y will be V naught sine theta, or 20 meters per second times the sine of 30. This one we can do right away. Sine of 30 is 1/2, so we're just going to get 10 meters per second. And let's write down everything to at least 3 sig figs. Okay, now we need to compute V naught x. So we're going to have 20 times cosine of 30, and to 3 sig figs we obtain 17.3 meters per second. All right, now we can proceed. So let's ask ourselves, first of all, how do we calculate y top? We might be tempted to go right to the y equation. So let's try writing the y equation. And let's put a note here, what we're seeking here. Y top. So we write the y equation. Y equals V naught y t minus 1/2 gt squared. And we see we can compute a value of y only if we have the initial y velocity, which we do, the y component, the time, and gravity, and we don't have the time yet. But it will be true that y top will equal V naught y times t top minus 1/2 g t top squared. So if we can find t top, we can come back and compute y top. But we don't know t top yet. So, what is t top? How do we get at that? Well, if we look at our equations, we notice that 3 of them have time in it, not just the y equation. The x equation and the vy equation both have time. The x equation won't help us at all because although we know v naught x, we don't know time. Time is what we're looking for, and we don't know x, the distance from there to there. So we can't compute t top that way. So let's take a look at the vy equation. The vy equation is this, and we do know v naught y and we know g, and in fact we do know vy at the very top of the trajectory, because right here the instantaneous velocity is horizontal, and at this point we can say that vy is 0. So we can write that 0 equals v naught y minus g t top. Then adding g t top to both sides gives us g t top equals v naught y and now we can solve for t top. T top will equal v naught y divided by g. So we can put in the numbers. We calculated that v naught y is 10 meters per second. And we'll divide by g, which we'll take as 9.8 meters per second squared. And we'll assume that this is good to at least 3 sig figs when we do our calculation here. So we need our calculator. And we have that 10 is to be divided by 9.8. And we obtain a time of 1.02 seconds, which, if you look back at the simulation, was in fact the time that we computed, or that computed, for the projectile to get to the top. All right, very good. Now let's move on and compute y top. So y top will therefore be v naught y t top minus 1/2 g t top squared, and we put all the variables in here. And compute. The first, we can calculate that very quickly. That will give us, after the seconds cancel here, 10.2 meters. And the second part is going to come out to be about half that. In fact, it will be exactly half that. And you can see that we have 1.02 squared, which is going to be just a little greater than 1. And this part will be just a little bit less than 5, and so the 2 will compensate, and we're going to come out, and you can check it on your calculator if you want, at 5.1 meters. And so in fact the result is going to be 5.1 meters. And that, you may recall, was in fact the maximum height that our first simulation achieved. All right, so that takes care of t-top and y-top. Now let's move on and ask what the range was and what was the landing time. Well, when we see x here, we might think, all right, all I need to do is compute x from the x equation. Which would be this expression. But note that we don't know TL yet, so we can't quite compute x yet. We need to seek TL first. So how do we get TL? Well, we can note the following. At landing, y equals 0. So, in fact, we can use the y equation, if we'd like, to find t land. All right, the y equation then is going to become 0 equals v naught y t land minus 1/2 g t land squared. This equation has quadratic form in t, but you'll notice there's no non-zero constant term in this equation. So in this case, we can actually solve this equation for TL without having to use the quadratic equation, which is nice. There are a number of ways to accomplish this. The way I'm going to do this is factor out a factor of TL from both sides, or from the right-hand side. All right, and now we have that 0 equals this factor in parentheses times this factor. Well, the only way that this can be true is if either or both this factor and this factor equals 0. So this can be true only if this is 0 and or this part is 0. Well, TL equals 0 is just the launch time. So it's true that y is 0 there, as this equation asks for, but that's not obviously not the time we're interested in. So the root that we're interested in must be from this factor. So now we'll set that part equal to 0 by itself. And now we'll solve for TL. We can do this by adding 1/2 GTL to both sides. We obtain this. Then we can multiply both sides by 2 divided by G. And that gets rid of the 2 there and the G there. And then we can flip the result around. We can see that TL is going to equal, make this clear here, that's a G there. TL must equal 2 V naught Y over G. And you'll notice that that's exactly twice the value we got for T-top. T-top came out at 1.02 seconds, so here we're going to have to obtain 2.04 seconds. And you may recall that's actually the time of flight that we calculated, or that the simulation calculated when we first looked at the simulations. All right, now we can compute the range. So here we have to use the fact that V naught x turned out to be 17.3 meters per second. And we multiply that by our 2.04 seconds. Seconds cancel. We bring up a calculator. We have 2 times, actually clear that, 17.3 times 2.04, and to 3 sig figs we obtain 35.3 meters. Which is just over 35 meters, which is very similar to the result that the simulation produced. Okay, now let's ask, what is the landing speed? Well, the landing velocity is a vector. Think about the projectile comes down. Just before it hits the ground, it has some final velocity, which we could call V, the landing velocity vector, VL. That's going to be composed of 2 pieces, Vx land and a Vy land. Now, from our discussion before, we know that through the entire trajectory, the x component of the velocity always remains at v naught x. And we're looking at the velocity of the projectile just as it hits, or just infinitesimally before it hits. So it's still, this velocity is still part of the usual trajectory characteristics that we're calculating. It doesn't take into account, for example, if the projectile hits something when it hits the ground. It's just how is it moving just as it hits the ground. So this is still true, that the x component of v will equal v naught x. So we're okay with that, and we know that is 17.3 meters per second. But VLY we don't know yet, but we can use the Vy equation. The Vy equation was this, and so we can substitute the value of TL here, and that will produce VYL. And then once we have VYL, then we can use the Pythagorean theorem to calculate the magnitude of VL. All right, so V naught Y was 10 meters per second. And our time of flight, which barely fits in here, was 2.04 seconds. And one of these seconds will cancel, although I didn't put the seconds here in properly. And let's go ahead and compute that. So we have 10 minus 9.8 times 2.04. And what do you think the answer is going to come out to be? Think about it for a second. Remember, V naught Y was 10 meters per second upwards direction, but here we are at the end of the trajectory. So by symmetry, you might guess that VYL is equal to minus V naught Y. So let's see the result. And in fact, if you look at that to 3 sig figs, indeed, that's minus 10.0 meters per second. So it does equal minus V naught Y, as we might expect. Okay, now we can compute the final speed. By the Pythagorean theorem, that's given by, actually here we go, VXL squared plus VYL squared. VXL was 17.3 meters per second, and VYL is what we've just computed. It's a minus 10 meters per second, but it gets squared. So the squaring will remove the sign. And if we calculate this out carefully, then we'll have 17.3 plus 10 squared, taking into account that the minus sign is squared out. And then we raise that to the 1/2 power, and we obtain 19.982242 and so on. And to 3 sig figs, if you round that up, you'll see that indeed we get 20 meters per second. All right, now we need to compute the landing angle. So our projectile is landing with some landing velocity VL, and we've computed its components, VYL and VXL. And we're seeking this angle here with the x-axis. But note that if we put the components together, we form a right triangle here. And that is VYL here as well. So we have VXL, VYL, and VL. And we can see that the tangent of theta will be the opposite over the adjacent. So it will be the opposite here over the adjacent. So theta will be equal to the inverse tangent of this ratio, And we can put in the numbers here. VYL is minus 10 meters per second. VXL is 17.3 meters per second. The units cancel. And let's see what happens when we have this inverse tangent with a negative sign. You may recall that when we were discussing vectors and how to compute the angle, that there's an ambiguity that comes in when you have a minus sign. So we're going to compute the arctangent of minus 10 divided by 17.3. And the computer gives us minus 30 degrees. And to 3 sig figs, minus 30.0 degrees. Okay, and this makes sense because we can interpret this as being minus 30 from the x-axis, that is, taking the angle in a clockwise fashion. And that's what generally calculators do. Calculators don't know really, they can't tell whether the minus sign was associated with the upper number here, the y component, or the x component, despite the fact that we know that. So the calculator just assumes that it's basically the number on the top that's the negative number, and so that implies an angle moving clockwise from the x-axis with a negative sign, as opposed to an angle in the second quadrant that would have a negative x value and a positive y. All right, so, but in any case, we see that this matches minus the launch angle, which we can call theta naught. And that confirms the nice symmetry in this problem. So let's consider another example, but this time let's launch horizontally that is with theta equal to 0 from an elevated position. That is, we'll choose that y naught will be greater than 0. Okay, before moving further, let's look at a simulation first and get an idea of how this projectile is going to behave. So here the simulation is set up to launch with v naught equal to 20 meters per second and at 0 degrees and at an elevated position 10 meters above the ground. All right, let's see what happens. We see that the projectile moves out to the right and then slowly falls and then finally hits the ground just shy of 30 meters. In fact, the range was, to 3 sig figs, 28.6 meters. The time of flight, the total time of flight, was 1.43 seconds, and the final speed was 24.4 meters per second. So let's see if we can calculate these three numbers from scratch and work out how this problem differs from the previous one. First, as always, we'll go ahead and draw our coordinate axes and draw our problem, and then we'll write down the equations and proceed. So this time we're going to launch from a position where y naught is equal to 10 meters. And v naught is equal to 20 meters per second. And our trajectory is going to look something like this. And we're going to ask, what is the range? What is the time of flight? So XL and TL. And we'll also ask, what is the speed with which it lands? VL. And finally, let's also compute the angle with which it lands. Unlike the previous example, in this example, we can't necessarily expect that VL will equal our initial velocity because we have a different altitude at landing than we did when we launched. And we have no idea a priori what the range and time will be, or the angle. Okay, let's proceed. The first thing I would like to point out, very importantly, is that if we break our initial velocity vector down, then the y component is going to be 0. So you can see that simply because the initial velocity vector is horizontal and has no y component. But just to see how the math works out, let's go ahead and compute it. By trigonometry, v naught x would still be equal to v naught cosine theta, but theta here is 0 degrees. So we would have v naught times cosine of 0, and cosine of 0 just equals 1. So that's just going to equal v naught. So v naught x just equals v naught, and therefore 20 meters per second. V naught y, on the other hand, is equal to v naught sine of theta, and so will be v naught sine of 0, but sine of 0 is identically 0, and so v naught y indeed is 0 meters per second. We now proceed to write down our equations for x, vx, y, and vy. Let's start with vx. That is the x component of the velocity. Here, as always, because there is no acceleration in the horizontal direction, vx again will remain fixed at v naught x. And in fact, we know right away what that is. That's 20 meters per second. X, likewise, because there's no acceleration in the x direction, and because x naught is equal to 0, still, we immediately have that x equals v naught x. That is, if we were to write out x naught plus v naught x t plus 1/2 ax t squared, the first and third terms would be 0, and we still have just this. And this is exactly what we had in the last problem as well, and so is the first line. So we can see that the equations for vx and x are identical to what we had in the previous problem. But now we begin to get some differences. For vy, vy would normally equal v naught y minus gt, but v naught y is 0, so we just get the minus gt part. So we get a simple equation for the y component of the velocity. That is, just to make sure you understand, the vy equation would normally be this, but the v naught y component is 0. And y, well, here y naught is equal to our initial height, and so we have to keep that because it's not equal to 0. So we have y naught, we have to retain that, plus we'll have normally a v naught y t term, but that is going to be 0, and then we'll have our 1/2 gt squared. All right, so let's just look back at really what's going to happen here. Our projectile is starting off here at y0, but it's only moving horizontally initially. So its initial velocity in the y direction is just 0. It's just heading horizontally. And indeed, if we put in t equals 0, we see vy is 0. But as time increases, the y component of the velocity is going to start to develop a negative component. And if we look at, say, a moment like right here, the instantaneous velocity will look something like this. We'll see we've developed a piece vy pointing down, and the vx piece will remain locked at v0x. All right, so basically, this projectile is essentially, as far as the vertical part, falling from rest. It's basically drifting to the right at a constant rate and falling from rest vertically. And in fact, if we happen to move into a reference frame that was moving at a constant velocity v0x to the right, this projectile would simply seem to be falling from rest from the position y0. But as seen in the particular reference frame we've chosen, that these coordinate axes represent, our projectile appears to arc off to the right. All right, let's summarize our equations one more time. Vx equals v0x, and that's constant. X equals v0xt, which increases linearly with time. Vy equals minus gt, which decreases linearly with time. And y equals y0 minus 1/2 gt squared. It's important to contrast this with the equations we had before. In the Vy equation before, we had a v0 y term, which is no longer present. And before, in the y equation, there was a v0 yt term, which is no longer present here. But instead, we have a non-zero y0 term here. So these equations are substantially different from the previous problem. Now let's ask, what is the range and what is the landing time? The range we could immediately write would be equal to v0x times the landing time, the time of flight. But we don't know the time of flight yet, so we can't use that yet. So let's figure out what we do know. We do know that at landing, y equals to 0. So, subbing into the y equation, we obtain this. And now adding 1/2 gt squared to both sides, and this is the landing time here, we obtain this. And now multiplying both sides by 2 divided by g, we obtain that TL squared must equal, I'm going to rearrange this slightly, 2y0 over g. And then finally, that TL is equal to the square root of 2y0 over g. And now we can actually compute the time of flight, or the landing time. So we put our initial height, y0, in there, acceleration of gravity. We bring up a calculator. And we have 2 times 10 divided by 9.8 all to the 0.5 power. And we obtain that the time of flight to 3 sig figs was 1.43 seconds. And if you recall, that's exactly what the simulation showed. Now we can compute the range, XL. V naught x was 20 meters per second, and this occurs for 1.43 seconds. So if we multiplied 1.43 by 10, that would be 14.3, and then by 2 again, so that will be 28.6. And that indeed was the range that the simulation predicted. Okay, now we need to compute the landing speed. So our projectile comes down and hits the ground with some final velocity, or the landing speed. And the landing velocity is a vector, so it breaks into the 2 components as usual. The Vx component, and we'll call that the landing x component, so Vxl, and we'll have the Vy component, Vyl. And we're going to have to compute that before we can compute Vl. Vxl, though, we know, as usual, is still locked at V naught x, which here is 20 meters per second. All right, now how to compute VL? Well, we go to the Vy equation. The Vy equation here is just equal to, or gives, minus gt. So Vy at landing will be minus gtl, and now we compute. So we have a minus 9.8 times a 1.43, and that's going to give us to 3 sig figs minus 14.0 meters per second. Now, using the Pythagorean theorem, since Vyl forms the opposite side here of this triangle, and Vxl is the adjacent, we can use the Pythagorean theorem to compute VL. So we have 20 meters per second squared plus a minus 14.0 meters per second squared. Of course, the minus sign will square away. So we compute. And that gives us 24.4 meters per second. Let's take a look at the simulation. And that agrees with the figure here, 24.4. Okay, let's now compute the landing angle. The landing angle by this triangle will then be the arctangent or inverse tangent of of VYL over VXL so we have minus 14 meters per second divided by 20 meters per second. The units cancel. So we have arctangent of a minus 14 divided by 20. Or a minus 35.0 to 3 sig figs degrees. Let's now consider a third example, and this time let's launch at both a non-zero angle and a non-zero elevation. That is, non-zero angle meaning we'll launch at an angle, so to speak. Let's take a look at a simulation first to get an idea of what's going to happen. This is our previous simulation. And in this we launched simply horizontally from 10 meters up. Let's increase the angle now to 30 degrees. So this is a little bit like our very first example in terms of launch angle and initial speed, but it's like the second example in that we're up 10 meters. So you can kind of think of this as somewhat of a combination of the two previous examples. All right, here we go. So we see that our projectile moves up into the air, so it does increase in height, and then makes a long arc down and hits the ground. And it does so about 48.1 meters from the launch point in terms of the horizontal range. And it achieves a height here which is given by 5.1 meters, but that's just the height above the initial launch height. So the actual total height above the ground would actually be 15.1 meters. So that's what we'll try to compute, is the 15.1 and this range 48.1. We also see that the time of flight came out at 2.78 seconds. And we see that our final speed here was 24 meters per second. Now you might be a little bit surprised that the final speed turns out the same as before. But there are some similar aspects of this to the previous problem. The initial speed here didn't change. We only changed the direction. So it's an interesting question as to why the final speed apparently came out to be the same. And I'll ask you to just think about that in the back of your mind for a while until later on in this presentation. Okay, so let's begin as usual by drawing our coordinate axes. And we'll label our initial height here as 10 meters, as we did before, but this time we're launching at an angle. So we have an initial speed still equal to 20 meters per second, and now we're launching at 30 degrees above the ground. All right, now we'll try to draw our trajectory as best we can using this funky roll of tape. And there we go. All right, so we can ask a number of questions, and one of them would be, what is the maximum height that was achieved, which we will call y top? And what is the time that it got to that position? We'll also ask, what is the horizontal range? That is, what is x land? And when did it arrive there in t land? And finally, as usual, we'll ask, what speed did it land with? And at what angle? So these are all the same questions we asked about the very first example. All right, now let's develop our equations. Let's write the whole set of generic equations this time, and then cancel out the things that are non-zero, or that are zero, if indeed there are anything. So Vx would equal V naught x plus Ax t, but there is no acceleration in the x direction in this problem, as usual for all of these problems. So again, Vx is just equal to V naught x. And so the x component remains constant. The x coordinate would equal x naught plus V naught xt plus 1/2 axt squared. Here, again, we still have x naught equal to 0, according to our diagram. But V naught x is not 0, so we have to retain that term. And of course, we don't have any acceleration in the x direction. So again, our equation for x is the same as all the previous examples, x equals V naught xt, which is comforting. Now let's look at the Vy equation. Vy equation generically would be V naught y minus gt. That is, a sub y is minus g. But in this problem, V naught y is not 0 in this time around because we're launching at an angle. So there is a y component initially of the velocity. And of course, the acceleration in the y direction is not 0. So we have to keep this entire equation. And the y equation would be this. And here we're launching from a non-zero elevation, so we have to keep y naught, and v naught y is not 0, so we have to keep this entire equation. So let's rewrite the entire set again. Vx will equal v naught x will equal v naught xt, Vy will equal v naught y minus gt, and y equals y naught plus v naught y t minus 1/2 gt squared. And this is, in fact, the most complicated set of equations we've studied to date. So let's begin. Let's first seek y top and t top. Well, as we saw with the first example, and actually just the first example, at the top, v sub y is equal to 0 because the projectile is just moving horizontally. So the Vy equation gives us, as it did in that first example, 0 equals v naught y minus g t top. And now we can solve for t top just as we did before. Add g t top to both sides, and we obtain g t top is equal to v naught y and t top is equal to v naught y over g. Now we need v naught y, and I'm going to use the fact that from our first example we calculated v naught x and v naught y for the same angle and the same initial velocity, and so we can take over those numbers. There we found that v naught x is equal to 17.3 meters per second and v naught y is equal to 10 meters per second. So we'll simply take over those values. And this, so far, is also identical to what we found in that problem. And we obtain 1.02 seconds to the top point. Okay, now we go to calculate y top. And by the y equation, y top is given by this expression. And let's compare this to what happened in the first example. In the first example, we actually had these two terms, but we didn't have this first term. So the only difference is we're going to get an additional piece of height that came from the fact that we were elevated initially. So we have 10 meters here, and let's go ahead and fill in the details. We have 10 meters per second times 1.02 seconds minus 1/2 9.8 meters per second squared times 1.02 seconds, quantity squared. It's coming off the page there. So we obtain 10 meters plus this term gives us an additional 10 meters, 10.2 meters, and this term once again is going to give us a minus 5.1 meters. So let's take a look. This piece is the part we got from the initial elevation, and this piece in total will be what we get from the effect of the initial velocity upwards and also the effect of acceleration downwards. So in particular, this piece comes from having shot upwards a little bit, and this piece is the correction coming from acceleration. So we can put that all together. We can see that these two pieces are going to give us 5.1, and we add that to 10, we get 15.1, and that does agree with our simulation. Because we had 5.1 here, and that was relative to the launch point, so we would have 15.1. All right, now let's compute the total time of flight and also the range. And then we'll compute VL and theta L. All right, well, at landing, y equals 0. And this is what we've used consistently to find the landing time before. So we have, using the y equation, 0 equals y naught plus v naught y t land minus 1/2 g t land squared. And we can put numbers in here and then try to solve for t. And you'll notice this time that we have a full quadratic equation here because we have a constant term, a linear term in t, and a quadratic term in t. All right, let's use the quadratic equation. Our quadratic coefficient for the squared term, a, not to be confused with acceleration, will be minus 1/2 g. The b term will be our v naught y, and our c term will be y naught. So by the Pythagorean theorem, TL is given by minus b, sorry, not Pythagorean theorem, by the quadratic equation solution, TL is given by minus b plus or minus the square root of b squared minus 4 times AC, all divided by 2a. And now we substitute these values in. So we get a minus v naught plus or minus. We're going to have a v naught squared inside, minus a 4. A is minus 1/2 g, and c is y naught. And then we'll have a 2 times minus 1/2 g on the bottom. Inside the square root, the minus signs cancel, and the 4 will partially cancel the 2. These 2's will cancel, but we'll still have a minus sign on the bottom. And then we can multiply the top and bottom by -1 to get rid of the minus on the bottom. That will cancel the minus here, and the plus or minus remains a plus or minus. And so we obtain the somewhat simplified expression as follows. Now we can plug in and find TL. V naught y is 10, and here I'll put in the numbers without the units, just to move things along. So we'll have 10 plus or minus the square root of 10 squared, minus 2 times 9.8, 10, as well here for the initial elevation, divided by 9.8. And we have to see here about the signs, about whether we take the plus or minus. Oh, and that's a plus right there. And let's make the initial observation here that this second part here, the square root of 10 squared plus this stuff, is going to be greater than 10. So if we take the minus sign, we're actually going to get a negative time. And that clearly is not going to be the landing time. So for our calculation here, we'll take the plus time. So we have, doing this all at once, 10 plus the square root of 10 squared plus 2 times 9.8 times 10 I have to raise that second set of parentheses to the 1/2 to take the square root, close the parentheses on the whole numerator, divide by 9.8, and we obtain 2.78 seconds, which, if you recall, agrees nicely with our flight time from the simulator of 2.78 seconds. Now we can compute the range. Which is just given by V naught x TL. And so we have 17.3 meters per second times 2.78 seconds. Seconds cancel. We bring back our calculator. And we obtain 3 sig figs 48.1 meters, which does in fact agree exactly with our simulation. Okay, now we can proceed and calculate the landing speed and the landing angle. So as we've done before, we'll have to compute the components of the landing velocity first, Vxl and Vyl, and then compute VL. And Vxl, as in all the other problems, just remains fixed at V0x, or 17.3 meters per second in this case. VL, however, has to be computed. So Vyl by our VL equation equals V0y times, or V0y minus GTL so we have 10 meters per second minus 9.8 meters per second squared times 2.78 seconds. And so we obtain 10 minus 9.8 times 2.78 and we obtain a minus 17.2 meters per second. And now we can compute VL. By the Pythagorean theorem, that's the square root of Vxl squared plus Vyl squared, or the square root of 17.3 squared plus 17.2 squared, where I've squared out the minus sign and I've left out the units here for brevity. And so we'll have 17.3 squared plus 17.2 squared, similar but not quite the same numbers. Take the square root, and we see that the projectile hits the ground with a speed of 24.4 meters per second, which is not only what the simulation predicted, but is also what we got in the previous problem, for reasons that I've asked you to ponder. Now, although VL is the same as the last problem, it will turn out that theta L is not. So we'll have to compute theta L, and using the geometry, theta L will be the inverse tangent of the opposite side over the adjacent. So it will be the inverse tangent of minus 17.2 divided by 17.3. So we have arctan, and it's a minus 17.2, so I'll put that in just for good form. And we get very close to 45 degrees, but not quite. Looking back at our simulation, this simulation actually is scaled with equally scaled axes, and you can see this angle of attack here, or angle of landing, does indeed look very close to 45. Recall what happened when we launched at 0 degrees. We obtained a shallower angle, even though the landing speed was the same. Let's now undertake an analysis of some special points about what's happening with these different examples. And we'll call this analysis of trajectories using results for flight time, range, etc. Okay, the idea here is to develop some insight into what's going on besides just calculating these specific parameters. All right, let's first of all, let's look at the range for projectiles landing at the same elevation as the launch. So that's this kind of problem. So we're given some V0 and some theta, and we obtain a range given by XL and also a time of flight, TL. So let's take a look. How does XL depend on V0 and theta? Previously, we obtained the following results. That is, in example 1. We found that the landing time, or time of flight, was equal to 2 times V0y over g. Note that this depends only on the vertical component of the velocity. That is, this is independent of V0x. It doesn't matter that, therefore, how fast the projectile is moving horizontally. The time of flight only depends on how fast it's moving vertically. And that makes sense because the projectile is just drifting to the right at a constant rate as far as the horizontal motion goes. And what determines when it lands is when it comes back to y equals 0. It doesn't matter what x is. So it could go straight up and down, or move just a little to the right as it goes, or go far to the right. We would get the same landing time. All right, for XL, we found, in fact, in all cases, that XL was equal to V0x times t land. Although this expression was the same for all three examples, this expression was only valid for example 1. Example 2 and example 3 gave us different expressions for TL. So now let's put this symbolic expression for TL into this equation for XL and see what we can obtain. And then rewriting it slightly. We see that we find that the range, which I'll write again here, is equal to 2 times the product of the x and y components of the velocity divided by g. Okay, going further, we can substitute in the trigonometric expressions for V0x and V0y. Simplify somewhat. I'll change the order of things a little bit. Now this is an interesting result right here. What this tells us is that for a fixed angle, XL depends quadratically on V naught. That is, if we, for example, doubled the initial speed, we'll actually quadruple the range. The projectile will fly 4 times as far with just double the speed. Now this might seem a little puzzling, but then let's consider why that's the case. If we double V naught, we'll actually double both Vx and V naught x and V naught y. And that means, first of all, doubling V naught y will double the time of flight. So for XL, we'll have double the time of flight, and V naught x, the horizontal speed with which the projectile is traveling, will also be doubled. So both of these quantities will be doubled, so XL will be quadrupled. So we can kind of get a feel then for how XL depends on V naught, and in a second now then we'll also look at how it depends on theta. All right, let's save that result. And now consider that from trigonometry, it turns out that 2 times sine of theta times the cosine of theta is equal to the sine of 2 times theta. Well, we have a sine cosine factor in our expression for XL. So from here, let's divide through by 2, and we can rewrite this as 1/2 times sine of 2 theta, and therefore XL, which we found previously, equals 2 V naught x squared sine theta cosine theta all over G, can be rewritten subbing in 1/2 sine of 2 theta and then canceling these 2's as V naught squared sine of 2 theta all over G. Okay. Now this expression can be used to prove the following nice fact. For fixed V naught, it turns out that we'll get the greatest range at 45 degrees. Let's see why that's the case. Consider the sine function. At the moment, just consider sine of theta instead of sine of 2 theta. Sine of theta looks like this, and it has its maximum value, which is a value of 1, at 45 degrees. Sorry, at 90 degrees. If instead we graph sine of 2 theta, what the 2 theta does is compress the range. So in fact, sine of 2 theta will have its maximum at 45 degrees, the angle that I first accidentally mentioned. That is, if you put in 2 times theta at that point, you'll have 2 times 45 degrees which equals 90. So we can see this expression for XL will have its maximum value at 45 degrees. That is for keeping V0 fixed. We can also look at this graph a little bit more carefully and see something else. Let me redraw that. The sine function is symmetrical about this point. So if we move a few degrees to the right, we'll come down the same amount than if we move a few degrees to the left. So, for example, we should obtain the same range at, say, 65 degrees, which is 20 degrees greater than 45, and 25 degrees, which is 20 degrees less than 45. In other words, at 20 degrees, at plus or minus 20 degrees, plus 45 degrees. All right, let's see if this works out in the simulations. Okay, let's bring up the simulator. And let's first explore the finding that we had that doubling the initial speed while holding the angle constant should in fact quadruple the range. So let's begin with our original old trajectory here with 20 meters per second at 30. So go ahead and run that. And we obtained a range here of 35.3 meters. So if we hold that and we double the launch speed to 40 meters per second, then our prediction is that we'll get about 4 times 35. 2 times 35 is about 70, so we'd get 70.6. And doubling that again, 141.2 to be exact. And it looks like numerically we're just shy of that, but that's basically the right result. So we can see this dramatic difference. Just doubling the velocity took us much, much further. All right, let's go back and consider our original launch speed here. And now let's explore what happens with the angle. Let's first launch at 45 degrees. Our analysis suggests that this will give us the maximum range. So at this angle, we obtain a range of about 40.8 meters. Let's hold that, and let's back down a little bit on the angle. Let's back down to 35. And we see, indeed, we fell shorter. And if we go even smaller, we go even shorter. All right, let's go the other way. Let's do our 45-degree trajectory again. Now we'll hold. Now let's increase the angle. So we'll take it up to 55. And we see, again, we're a little shorter than the 45. So that is consistent with the idea that 45 gives us the greatest range. Let's go up to 65. And so forth. Okay, next, let's take a look at the finding we obtained by looking at the symmetry of the sine function. That is, suppose we start with our 45-degree trajectory. Our analysis suggested that if we go up or down an equal amount from 45, we should obtain the same range. So let's go up to 65. And hold that trajectory. And now let's go down to 20 degrees below 45, 25. And indeed, we see we obtain the same range. Let's go just 10 degrees below 45. That is 35. And then go 10 degrees above 45, 55. And we see that indeed this pair of trajectories also had the same range. And for good measure, let's put in our 45-degree trajectory again. And that gives us a very visually nice looking set of trajectories here. Okay. Now, let's next consider something we saw before that I asked you to ponder. Specifically, we noticed that in many cases it appeared that VL, at least when V naught is fixed, is independent of the launch angle theta. Now, this was surprising, or is surprising, because when we change theta for fixed V naught, we can obtain different landing angles and different ranges and different times of flight, and yet that it works out that VL turns out to be independent of theta. Let's take a look at the simulator and see if we can see this in action. So here's our simulator with the same setup that we had for problem 1 or example 1. And let's go ahead and simulate that. In here we obtained a landing speed of 20 meters per second, which was the same as our initial. Now here it seems reasonable just by symmetry that this final speed is the same as the initial speed. So it makes sense that if we change the angle that we're going to get the same final speed. But let's hold that trajectory and pick a different angle. Pick 55 degrees here, just to be sure. So we obtain now a different time of flight and a different range, but yet the final speed is still 20 meters per second. Let's take one more. Let's take an angle of, say, 20 degrees. Very shallow. And here too, we see we obtain a final speed of 20 meters per second. All right, let's take a more non-trivial example. Let's elevate our launch position up 10 meters. And let's see what we get. We'll start with this 20 degrees. And we obtain a final speed here of 24.4 meters per second, which should sound familiar from what we had seen before. Now I'll hold that. Let's increase the launch angle. Let's try 30. Now we land at a different point. We have a different time of flight. Our landing angle is slightly different, but yet again, our final speed is 24.4 meters per second. Let's pick a very different angle. Let's launch at, say, 65 here. Now we have a much shorter range, a much steeper angle, a very different time of flight, but yet again, our final speed is 24.4 meters per second. Let's actually pick a negative angle. Let's launch in a downwards way, say minus 20 meters per second. So we obtain this trajectory. This looks very different qualitatively from these others. And a very short time of flight, a very short range, and yet the final speed is still 24.4 meters per second. Okay, let's see if we can prove that this is the case analytically. That is, at least for fixed V naught. And let's take the case with an elevated position, which is clearly the most complicated. So again, what we're trying to prove is if we launch our projectile from some elevated position, say the top of a building, that it doesn't matter what our angle is, we may obtain different trajectories, but in all cases, the landing speed will turn out the same. These will be the same if these are the same. So if these are the same, then these are the same. Okay, here's our proof. Previously, we found that the landing time was given by this rather complicated looking expression. And we're going to need this because what we're after here is computing VL. And VL is equal to, by the Pythagorean theorem, Vxl squared plus Vyl squared. And Vyl will depend on TL. Because by the y equation, it's given by the Vy equation, it's given by this. So what we're going to have to do is take this expression, plug it in here for TL, and then plug the result in here and calculate VL and see what happens. But let's consider, first of all, just this piece. Let's put in our expression for TL in here. And as ugly as this expression is, some very nice things are going to happen right away. Can you see it? First of all, the g's cancel. Then the v naught y's cancel. So Vyl just equals this. So then immediately we have that Vyl squared is equal to just what's under the square root here. And that's a much simpler looking expression. Also, Vxl is just equal to V naught x. So VL, which equals all this, VXL squared plus VYL squared, reduces down to V naught x squared plus V naught y squared plus 2g y naught. Okay, now I'm going to slightly regroup what's underneath the square root here. And I can always do that because adding is associative. It doesn't matter where the parentheses are. But then you'll notice something. We obtain this quantity here, V naught x squared plus V naught y squared. And that is none other than simply the initial speed squared. So it turns out that VL reduces down to this expression. And you'll notice that theta appears nowhere in this expression. This only depends on V naught and Y naught, and also on G, that is how high above the ground you're starting in terms of assuming that this can be taken constant, assuming we're not moving too much, but say if you were to launch 100 miles up in the atmosphere, G might be a little different. But otherwise, VL really only depends on the initial speed and the initial height, and not theta. So that completes our proof. But now let's look at the problem in a little bit different way. We can explain this with energy concepts. Now we haven't gotten into energy concepts much yet, but simply put, the total energy of something like this can be expressed as a combination of its potential energy plus its kinetic energy. And we're going to see later on in the course that the potential energy here can be expressed as mg times the height, and the kinetic energy can be expressed as 1/2 mv squared. And in fact, in particular, our initial total energy will then be mg y naught plus mg v naught squared. But an interesting thing happens then, because within our assumptions, we're neglecting drag from the air, and in that case, we can assume that the total energy of our projectile is conserved. What that means is, at the top here, our projectile, which is being launched at some angle with some v naught, will have a certain amount of kinetic energy and a certain amount of potential energy. And as it flies through the air, that total amount of energy won't change. The amount of energy we'll have here, which we could call the final kinetic energy, will still equal the initial kinetic energy. The final total energy will still equal the initial total energy by energy conservation. Now, the final potential energy here, because we're at a zero height, will be zero. So the final energy will simply be the final kinetic energy, which equals 1/2 mv final squared. And it doesn't matter what angle we launch our projectile at. no matter what we do, the final kinetic energy, or the final total energy, will be given by this, and that will always be equal to whatever initial total energy we had at the top. So, because the initial total energy is independent of angle, it only cares about the potential energy and the kinetic energy doesn't have any dependence on the angle, then the final total energy will be independent of the angle, and hence the final kinetic energy will be independent of the angle, and hence the final velocity, or what we've actually been calling VL, will be independent of the angle. So we can understand the independence of VL on theta through energy concepts instead of the direct computation we've made. And you'll notice this argument's quite a bit shorter than doing all the math, and this shows the utility of using energy concepts over kinematic concepts. And we'll see a lot more of that kind of thing when we get to energy concepts later in the course.